Hi everyone, for this video, I'm going to be going through worksheet 2.2a. Those of you who have submitted the soft copy, please go in, take a look, see the feedback that's been given to you. For those of you who, I'm going to use the late submission people, I'm going to mark through your scripts so that everybody can see and learn from each other as well. By now, you have received your hard copy worksheet 2.2a, all corrections or learning points to be recorded there. And separately also your textbook should be open to the portion on topic 2.2. Okay, so we're going to talk about the different types of volcano. Where we last left off in class, we were talking about this, the volcanic explosivity index. So I brought up the idea that when a volcano erupts, these are the two things that is released, whether it's lava, which is the red liquid thingy that you can see that's very hot, that you usually see in movies, but in reality, actually there's also this thing called tephra and pyroclastic flow. Now these are technical terms, and like I said, not to worry, we'll be going in greater depth for all of them later. But one good thing is most of you can correctly identify that this is actually more dangerous because it is a bit more sudden. You can see here, right? The explosion is something that is more unexpected as opposed to this one that's happening. The flow of the river of lava is just like that, so you can actually see where it is and maybe even sidestep it, yeah, or develop around it. No, not like that, but you can always just sidestep it, so it's not as dangerous. So you can see the main difference here, right? While there is still dust and ash in the air, you can see here, this is nothing by comparison to this that's happening. Right, when it explodes, there's a whole bunch of things that happens. So this is what's measured as the volcanic explosivity index. Oh no, it's doing it again. Okay, I'm continuing. So you've already seen those things, the tephra and the lava. So that's the reason why a volcanic explosivity index is something that people measure. If say you want to compare one volcano to another, which one is more dangerous than the other, they measure using these three indices. Indices meaning the three different index. Say for example, you want to measure how successful a person is. Maybe you can measure by the income, by the length of, I don't know, marriage, length of being able to hold a job, whatever it is. So there are ways to measure a person, whether it's successful or not. Same thing when it comes to saying something is explosive. How do you measure it? We already went through in class. For an earthquake, it's very easy. It's the magnitude, it's how bad the shaking takes place. But for a volcano, there are many ways for us to actually measure. So it's a combination of three things. First one is the volume of ejected material. How much is being released when it is being released? Because if say for example very little comes up, means it's not that significant at you, right? Second one, if you want to measure how explosive the ejection is, you also see how high up there into the atmosphere does it go. So the height of the eruption cloud. And just like when we talked about when it comes to the earthquake one, it's a bit hard if you just measure one moment versus something else that erupts and non-stop keeps erupting. Right, so the duration of the eruption as well. So total 3 different index. So you need to know lah. The higher the duration, the higher the height, and the higher the volume, it means the more explosive the thing is. So it's a combination of all three. Okay, and to make life easy, just like when it comes to Richter scale and moment magnitude, this is also logarithmic, meaning 10 times more powerful as you move up by 1. It's just that unlike earthquake, where it measures from 0 to 10, this one is only up to 8. So maximum only 8 so far lah. God knows, right? Maybe when it comes to the end of the world, that kind of thing, when the biggest volcano eruption, it may be worse than an 8. Maybe then it can be a 10 lah. But by then we all die already lah. Okay, so this is what's considered an explosive volcanic eruption. Now I can see in your submissions, the homework that you're given, most of you have already started using this term effusive. Okay, effusive, if you're not familiar, is this kind. It's the kind where it's basically is like bubbling up of lava. That's about it. So there is nothing too explosive about it. It's like a gentle eruption in a way. This one of course is fast forwarded. This in reality it doesn't flow that fast. Okay, so for this one, where does it fall within the VEI scale? This is considered 0 to 1. So not that bad at all. Okay. Alright, so finally I get to get out from PowerPoint. God knows why it has been doing weird things so far. It keeps drawing lines when I try to move next. But let's go into looking at your submission for worksheet 2.2. Knowing that there are different types of volcanoes out there, some with an explosive eruption, some with an effusive one. Then we take a look, what is the names of those volcanoes? Okay, so if you take a look here, right, the name, I'm going to use Zhengshan's one. I hope you don't mind. There'll be a bit more annotation on yours than the rest. So this one is a stratovolcano. That's the one that has the explosive eruption, the one that was on the right. Okay, the one with the effusive eruption, the one with the barely any amount of tephra releasing, stuff like that, that's called a shield volcano. So these two types of volcano will release two different types of eruption. Then we go into why is that so. So I already started off giving you the hint. The main reason why is because of the type of boundary that it comes from. Okay, so if you imagine here, the type of plate boundary for a stratovolcano is convergent versus a shield volcano which is divergent. Okay, so Bhavik, you're wrong, huh? It's balik. Okay, so if you take a look, right, why is that so? Because the lava that happens between the two of them is slightly different. So my first question is, how is lava formed? Right? A lot of you, okay, most of you can extract the correct information from the textbook. Some of you wrote the wrong thing though. So you've already been given a feedback, you already know where you went wrong. But I want to zoom in a bit into how the lava comes about. Because if you see on the left hand side of this video, which is over here, this diagram, this is a convergent plate boundary. OO or OC, both of them have this same feature called subduction. So when you subduct, effectively there is a rock, this crust, that is going underneath. So what happens in this location? This is the mantle layer, which is nothing like the crust layer, nothing like the atmospheric layer either. So this portion is going to be high temperature, high pressure. Remember, they are being pushed, right? When you squeeze something out, say for example, you're squeezing, wringing a towel, you're squeezing things out. Water, even though it looks relatively dry, like a dam kind of thing, it's relatively dry, you squeeze it in, water will come out, right? Same thing happens here, because if you imagine, the subducted crust is always oceanic crust, right? Oceanic crust, meaning within the pores of the rocks. Remember, these are all rocks. Within the pores of the rocks, there may be some water within them. The water doesn't flow in, of course, obviously, because there's still the crust here that is blocking it. But the rock itself, the oceanic crust itself, has some moisture, which under this high pressure, the water starts to come out from the rock itself. So once water gets released, if you realize that's the reason why we always draw two layers, right? There is an uppermost mantle. What happens is when this water enters this uppermost mantle, it lowers the melting point. And when melting point gets lowered in this environment where it can reach up to 3000 degrees Celsius, what happens is this mantle will therefore melt. When it melts, it forms magma, which then rises to form the volcano. Alright, so this is how the lava gets formed, again from magma. And the magma comes from the lowered melting point of the mantle, and that comes from the fact that there is water being introduced, and that comes from the oceanic crust. Okay, so this is what I'm looking out for in your answer. So you see that you got about 4 to 5 ticks here. Okay, so where do the points go to? Okay, first one, I want to take a look at the denser plate mass subduct. Preferred is I would like to see the word oceanic, because that's where the moisture comes about. Okay, so if we talk about it then, after it has subducted, high pressure forces the water out. Okay, and when the water is being forced out, it lowers the melting point of the mantle, which allows it to melt to form the magma. But again, the question is not asking you about the formation of magma, it's asking you about the formation of lava. Before we can consider it as lava, it has to release above the Earth's surface. So the dissolved gas makes it less dense and it rises through weak areas to the surface. Then it becomes lava. So these are the 5 points that you need to get in order for you to secure the correct answer here. Can I please have you take a look, see in your own version of your submission, what was the points that I missed? Okay, if you want to write this down, actually you should be writing this down for a hard copy lah. Like I said, to record learning, right? But please don't tell me you're going to rewrite everything under the sun. Okay? more important is for you to write down, especially the underlying portion, the key concept here. Okay, in an exam setting, am I saying that this one confirm will be a 5-mark question? No. This may well be just the whole thing, just 2 marks. Alright. So, yeah, please feel free to pause whenever. This is what happens at a convergent plate boundary. There is something that is missing here, something that is not mentioned in the textbook as much either. Is something that Vidyut brought up in the WhatsApp message in our group chat, if you recall. Okay, so he brought up this idea of silica content, which is something you've also already seen in your textbook. Okay, what happens here, right? We're talking about water being added. But the thing is, this rock, when you enter the mental material itself, is still high temperature, is still high pressure. The thing is, the rock also melts. But when the rock melts, it doesn't actually form magma. It just adds into the mental material. Instead, what it does is, it becomes silica, which is then added to to the magma. Because it's melting at the same place, you see, where the mental material melts to form the magma. At the same place, the crust, the oceanic crust that's subducted, also melts, which adds silica. And this silica content adds into the magma. This is important. I know right now it's not exactly required for this question, but I would like you to record this down anyway, because this is important, as in it will add to why the lava is so different between a convergent and a divergent boundary. Okay? So then we move on to the divergent boundary. Divergent boundary, where we find this thing called the shield volcano. This is when, remember these two diagrams? This is the OO divergent. This is the CC divergent. This is where you form the mid-oceanic ridge. This is where you form the rift valley. Mid-oceanic ridge. Okay? At this portion, not so much about introducing moisture, but rather we're talking about reducing pressure. Remember just now, it was you introduce moisture, high pressure forces the water up. That makes it easier for it to melt. But when it comes to a shield volcano at a divergent boundary, here there is no increase in pressure because you're not pushing things in. Right? If anything, if you remember what pressure is, I'm sure you learned from your lower sec science. Pressure is about the pressing force, you press downwards force. Right? When you move apart, there's now a gap. That means over here there is no more pressure because the weight is suddenly lost. Right? This means this area is suddenly low pressure, which also lowers melting point to form magma. Okay, so you can see here, right, the fact that if there is a crust, a continuous crust, it will continue to add weight because there's gravity, right, pulling on the mental material. But when there's a lobang, suddenly this area has got no more weight. So here there is a reason for the magma to suddenly melt because it is low pressure. What happens to this magma? You already know lah, it rises. But this is OO divergent. How then do you explain at a CC divergent? Because CC divergent is not there's a sudden loss of weight, right? But actually in reality it is. If you see, when this portion moves away from each other and this rift valley starts to go down, you can see here now the thickness is much lower. So the amount of weight that is exerting on the magma is now less. And when there is less, therefore this is again low pressure, lowering the melting point so that it can form magma. So in effect, as long as it's diverging boundary, it will form the magma in the exact same way. Okay, so let's take a look. I know these are expressions that's within the textbook, but let's take a look what are the key points that are being mentioned. Okay, when the crust stretches, the overlying pressure, there's a decrease in overlying pressure. Okay, feel free to add on. Why is it that there's a decrease? Because there is a gap, because the shallower depths of the rift valley gap between oceanic or the shallower depths of the rift valley area. Right, so there is decrease in pressure. These things cause the mantle material to melt to form magma. But once again, my question is not magma, it's about lava. So, because there is dissolved gas and is less dense, so it rises through the weak area and erupts as lava on the Earth's surface. That's the third point that you need. Okay, take a look at where your points are missing. But importantly, can I please have you add in why is there a decrease in pressure? So you don't just accept it as it is. Okay. Then I would like us to zoom out. Then we're going to just compare the difference between them. So you can see, right, the process definitely not the same. But it results in lava that's also different in characteristic. You can see here when it comes to a divergent boundary, there is no melted crust. Or rather none that is so fastly pushed in that it melts so fast to add the silica content. So what happens instead is that viscosity becomes different in characteristic. Viscosity, if you're not too familiar, I want you to imagine honey versus water. I actually brought it along with me to class the other day, but I was just not able to showcase to you. Imagine hand sanitizer, you know. Then you press the hand sanitizer, right? Then it flows on the surface. Versus beside it, you just pour a bottle of water and it flows on the surface. Same volume, but you can tell that when the hand sanitizer or honey, it is slower to move because of viscosity. The higher the viscosity, the more friction within the fluid. What happened here? Within the fluid. So it makes it slower. Okay, on the other hand, if it's low viscosity, there's very little friction. The water molecules are able to flow quite fast, so it results in higher speed of flow. Okay, again, when I see your corrections done, make sure that you're watching this video. I will be looking out for what are you annotating. Please don't tell me just go in a circle. Okay, how does this affect the volcano? So this one, most of you got this correct. Tall, steep and narrow versus short, gentle and wide. But I want to go through why that's the case. Okay, using this volcano as an example. Okay, before we look into Cheng Xuan's script, right? Let's take a look at this. Imagine this to be a convergent boundary. This one is a divergent boundary. Divergent boundary. Okay, so the first one is the lava that comes up. Same amount, imagine, right? It's the same volume of lava. Because this is more, here in convergent is more viscous. It will travel shorter distances from the vent, from the hole of the volcano. Okay, before it starts to solidify. Right? Again, you imagine if this is hand sanitizer or if this is honey that is pressed out of an injection mold, right? It's not going to travel far away from it before eventually it just stops moving. And when it stops moving, it cools down, it will then form a volcano. On the other hand, as a divergent boundary, it is less viscous. And when it's less viscous, it can travel further. Imagine injecting water out from a syringe, the water will just flow everywhere. Right? So it can travel further from the vent before solidifying. Okay, so this is one layer of, say, imagine this is a brand new volcano, a baby volcano. For the same volume of lava, you can already see a difference in height, difference in width, difference in shape. Add to it the fact that when it comes to a convergent boundary, it also has an explosive eruption. Where there is tephra, the dust, the ash, the debris, it also gets released together and it forms another layer above it. Right? On the other hand, at a divergent boundary, because this is an effusive eruption, there is no such thing. Or maybe there is, but very little. Okay? Then, maybe 5 years later, another eruption happens. So this layer is now solidified. Another layer happens, the lava burns its way through and it forms another level. Then again, there's the layer of dust and ash that settles to form the volcano. This is only the second eruption, as opposed to a shield volcano, where the second layer will just spread further outwards. Yeah, same volume of lava. Then it continues more and more and more until over time you end up with a volcano that looks like this. Now you realize I'm purposely drawing this. I want you to keep this in mind. This is what's called a crater. This is what's called a vent. Okay, and the lava flows out of a conduit. Okay, formerly known as a pipe. Your seniors will learn this as a pipe, but for your syllabus, you're referring to it as a conduit. Yeah, so this is where the lava comes out from, and you can see there's a difference in characteristic. This is after many years. You can see that for one, the gradient is gentle. The width is the of base is wide. The height is lower. Okay, but also another thing that you can see, there is a difference. There is a specific characteristic. Gradient gentle seems to refer to just a triangle shape, but it isn't. There's a particular shape here because of the fact that the solidifying is still uniform. Okay, so this is another shape that's also referred to as a convex shape. This is not within your textbook. I still would like you to write this down because it determines how you draw your diagram. There is a reason why I want to bring this up. I'll bring this up later on, but I would like you to please make sure when you're drawing there is convex shape. Okay. Then we bring into the idea of the stratovolcano, which is the one at the convergent boundary. Okay, so you can see this one looks like a shield, hence it's called the shield volcano. Here at the stratovolcano, again, it needs to have the crater. It forms a slightly different shape. Take a look at this. Okay, because the solidifying, it happens mostly at the top, mostly at the vent. It doesn't spread as far down. It becomes over time steeper and steeper and steeper. Yes, it's steep, but again, especially steep at the top. It doesn't get steep everywhere because otherwise the thing will collapse. Okay, so it's steeper gradient. The width is not as large. It's narrower. For sure, the height will be greater. Okay, but the important part of it is the shape. You can see it starts to curve. This is what's called a concave shape, which is something that I want to make sure is featured in your diagram as you draw it. Alright, and the last final point, this one is something that you can see in the diagram. So far they haven't really brought this up. I don't know whether it's in your syllabus anymore. Maybe if it isn't, I don't want to add in to confuse you. Let me find out a bit more first. But you also see that there are secondary pipes that's being created. See, your own the textbook diagram also has it. I don't know why they brought it up, but they never say to teach it. So yeah, just in case, I would like you to please draw this. Actually, it has to do with the viscosity as well. Okay, so I explain it anyway lah. So the reason why it's so high is because it's viscous, right? It doesn't want to travel far, right? The thing is, sometimes the lava is so viscous, before it can reach the top, there's just too much pressure, it burns a brand new path out. So effectively it forms more conduits, secondary pipes in a way. Then it starts to form all this. Okay, so let's take a look at the description. Explain why the level of viscosity in a stratovolcano, high viscosity, can lead to this kind of shape. Okay, so it erupts explosively with lava, ash and rock, which settle on the side of the volcano. Very good. Okay, on top of that, there's also highly viscous lava, travels a short distance from the vent before cooling and solidifying. Okay, so these are the key points that you need, and also If you see right within my diagram here as well, the reason why it's more than twice the height, besides the fact that it's viscous, it also has the alternate layers of lava, ash and rocks. So it's not enough just to say because of the lava that's why it's tall. It also has the alternate layers of ash and lava. Okay. So total, these are the 5 points needed for why a stratovolcano is so freaking tall. Okay, on the other hand, for a shield volcano, because it's low viscosity, it erupts effusively. That means there is very little dust and ash. You still need to bring it up because you're trying to explain why it doesn't contribute to the height of the thing. Okay, then you bring up the fact that less viscous lava travels long distance before cooling and solidifying, so it becomes a gentle volcano with a white base. Simple 3 points. Okay, in this case, again, if you see the command word here, right, explain why. So I'm asking you to explain the reasons why. I may ask you to describe the process. I may even ask you, and I purposely put them side by side so it's easy for you to see. I may ask you to describe the differences in their process, or explain the differences, or just simply put 2A to the 2B one, describe the differences between the two volcanoes. Many ways that this can be tested, but keep in mind, we need to know what the information is to begin with. Last one is to talk about the type of eruption. Now this one again is a term that I use more regularly with your seniors because it's a term in their syllabus. Yours has changed already lah. So can I please have you change this to effusive instead of gentle? Okay, of which Zheng Xuan, well done. Explosive for strato, effusive for shield. Okay, then let's talk about their viscosity. Because this viscosity, right, like I mentioned just now about whether it's hand sanitizer or honey, it has to do with the amount of air. You see here, right, the reason why the lava is less dense to begin with is because of the presence of air. Makes it easier for it to want to go up. Same, that's the reason why it don't have. What happened to it? Oh no, I put it here. That's the reason why, if you take a look here, this is honey. You can see in any jar of honey. Actually, as a matter of fact, maybe I'll even bring this to class next time around. The hand sanitizer, right, if you were to shake it, the air bubbles inside. It will stay inside there. If I were to blow through a straw, it will stay inside there because the air, the liquid is just too thick for air to escape. On the other hand, if you were to blow through a straw into a bottle of water, you know what happened, right? It will bubble right back up and it will just escape. That's the reason why different viscosity will have different amount of trapped air inside it. And that matters. Because if you see here, the reason why a stratovolcano has such an explosive eruption is because the dissolved gas cannot escape easily. What I'm expecting to see here, because explain why, right, is dissolved gas due to high viscosity. Of lava. That's why it cannot escape. But the thing is, even though it cannot escape, it wants to. Okay, so you imagine in the context of this type of volcano, as it travels further and further up the conduit, all the way to the very top, right? It's traveling up there, the gas bubbles, and the thing is, because the lava itself is so hot, right? What happens to air when it's heated up? It will expand until the very top, then it will pop like a bubble. And when it pops, that's when it becomes an explosive eruption. Yeah, so you can see here, the pressure will build up until eventually it escapes explosively, causing a violent eruption. Okay, so these are the 4 points that you need. Dissolved gas cannot escape because of the high viscosity. The pressure builds up. Would be good if you can see high heat, causing air to expand. But I think this is beyond your syllabus already, but it's okay. But the pressure builds up, for sure you need. Okay, then eventually it escapes explosively, as compared to a shield volcano, where there's a magma, the dissolved gases escape easily because as it leaves low viscosity lava. That means less pressure would build up. That means it's just effusive eruption already lah. Yeah. Okay, so this is basically it. This is a 30-minute supplementary for our lesson that was missed. I would like for the worksheet 2.2a to have been updated, not just with whatever that we is written in Zheng Xuan's script here, but also in your own, take a look at your own mistakes that you make in the soft copy Google Classroom submission. I want you to write in what are your mistakes. With regards to the diagram, I already drew them here. Feel free to pause, rewind, whatever it is. Okay, this one I only ask you for a labeled diagram. Okay, so I want you to take a look at your labeled diagram as the end product. Okay, that's about it. Alright, okay, this is something that we talked about in class. Rate of submission has been terrible. I would like this by Friday. Yeah, please don't delay this. I want you to have your entire weekend to yourself for you to revise, rather than you go and slowly do this everything over the weekend. I want this done by Friday. Okay, submit to me effectively. I just want to take a look at your corrections. I'll return this back to you the following week. Alright, see you guys.